Thank you, and thank you for the invitation. It's a really big pleasure to be here today. So I'm going to talk about optimal quantum algorithms for Gibbs states preparation. And this is joint work with Cambyse José in Paris and Álvaro Alhambra in Madrid. So let me start by motivating the problem a little bit, and then I'll also explain why I think this might be relevant for people interested in quantum optimal transport. So what are quantum Gibbs states? Well, in principle, you just take a big Hermitian matrix H, you exponentiate it, and then you normalize it by its trace. This Z over there is just trace, E minus beta H, the partition function. These states, they appear everywhere in physics because they describe states in equilibrium. So in statistical mechanics, they are all over the place. But they are significant much more beyond that. So they also appear in optimization, machine learning, many inference problems. So there are many reasons to care about these quantum Gibbs states. And in principle, given that many physical systems converge, if you leave them alone for a while, they'll converge to these Gibbs states. This is a very common process in physics. You'd also expect that it should be easy to simulate such states with a quantum computer, because at least one of the ways people like to sell quantum computers is that they allow us to efficiently simulate processes that occur in nature. So this is something that definitely happens in nature. So you'd think that, well, maybe if you give me a quantum computer, I'll also be able to simulate such states. Now, and classically, we have multiple ways of actually approximately simulating such systems. So when I say classically, you just replace H. Now, instead of big Hermitian matrix, just think of it as a diagonal matrix, but actually just like probability distributions on say, bit strings. And one of the standard methods to actually approximately sample from such distributions are Markov chain Monte Carlo methods. And these are studied to death and have been so for the last, 60 years, maybe even more. And we can show that in certain regimes, they indeed allow you to efficiently sample from such distributions. And also in practice, you see they work very well. People actually do this all over the place. And we would like to mirror this sort of classical success for the setting of quantum computers. So, and one way you could think of quantizing, say, a Markov chain Monte Carlo algorithm is by implementing some sort of dissipative time evolution. So a process that is in principle similar to the decoherence we heard about during the questions in the last talk. So this would be some time, some evolution of this time, e to the TL, where this is a so-called Limbladian, that if you apply it to any initial state you like, as time goes to infinity, it's going to converge to the Gibbs state you care about, all right? And, well, why should you care, maybe, if you're taking this quantum optimal transport perspective about this story I've been telling? So, of course, I assume that if you're attending this workshop, you have at least some interest in quantum optimal transport. The reason is that semigroup methods are extremely powerful if you look at classical optimal transport. So, having some sort of semigroup that allows you to converge to a certain distribution, and if you're able to quantify this convergence, you often get very nice inequalities related to optimal transport from that. So, for instance, you could get a transportation cost inequality. And from that, usually, you also get very nice concentration inequalities, say, for non-IID random variables, say, weakly correlated random variables. As far as I know, these sort of semigroup methods are maybe the most powerful we have to show concentration beyond this IID regime. So hopefully we can then combine these ideas also to get more and nice concentration inequalities for non-product quantum states, not necessarily probability distributions. And there are some works already in this direction by some people here in this room. And you have other physical applications which again combine ideas from quantum optimal transport and these convergence statements. For instance, you can show things like the so-called weak eigenstate formalization hypothesis by combining these ingredients. So there are lots and lots and lots of applications of semigroup methods in classical optimal transport. And what I want to tell you today is that over the last months, or maybe over the last year or so, we've been able to show also rapid convergence of semigroups for multiple quantum systems. So until maybe last year or so, there were very few examples of quantum systems for which we could show that these semigroups mix rapidly, okay? And this field is now progressing rapidly. So I think this should also motivate people who are coming more from this quantum optimal transport perspective to see if we can then also ride this wave and get some nice functional inequalities from these new proofs and new semigroups, okay? So hopefully this motivates you a little bit as to why you should care about this. All right. So let me show you first why we had problems in the past, why we were finding some issues in bringing, let's say, classical proofs to quantum systems about convergence. So the most standard way of modeling how a quantum system formalizes is through the so-called Davis generators, all right? So essentially what you get, and I mean, this is not necessarily recent stuff, and the idea from Davis is that you have some quantum system with your Hamiltonian H. It's coupled through a bath, and you assume it to be weakly coupled, and you have some jump operators. And then if you do some manipulations, and it's non-trivial, and some of them I also don't find that easy to justify, but let's not care about that. You can actually show that the dynamics of the system will indeed be of this e to the t L I showed before, where L has this form over here. These A omegas are the so-called jump operators, which are defined over here. So this is the so-called master.
What is the bracket? This curve bracket. What's it denotes?
This thing over here?
Yes.
This is the anti-commutator.
Okay,
Anti-commutator, yes. Oh, by the way, I should have said this before. I think there are people with very diverse backgrounds here, so please interrupt me if I mean, I'm going to use some notation which is certainly not going to be familiar to all, so don't feel uncomfortable in interrupting me. All right. Okay, so there are certain things we do like about the Davis generator. I don't only have hate for it. So for instance, it converges to the Gibbs state. So you can indeed show that as you let t goes to infinity, it will converge to this Gibbs state. And it satisfies a quantum version of so-called detailed balance. So many classical Markov chain algorithms, let's say Metropolis or whatnot, or Glauber dynamics, they satisfy a property called detailed balance, which essentially shows that the transition matrix of this Markov chain is self-adjoint if you pick the scalar product to be weighted by the probability distribution. And one of the possible ways of quantizing this idea is this property over here. So this guy is the evolution in the Schrödinger picture, and this guy is the evolution in the Heisenberg picture. And you have this equality once you weigh them with the square root of the state. And it turns out that this is equivalent with the generator being self-adjoint when you choose this scalar product between matrices. Okay, and again, this derivation works in this weak coupling limit, where the lambda again was the coupling between system and BAF. When this lambda is much smaller than omega, and okay, I should have said what omega is here on the slide again. Let me jump back. Omega is the difference between the energies of your Hamiltonian. And for classical systems, let's say you have some easing model or something like this, then and your energies are integers, then this omega will in principle be well behaved, will be of constant order. But for quantum systems, this can be exponentially small. So this is one of the reasons why this is not so well justified.
Is H finite dimensional or also infinite dimensional?
Even for finite dimensional ones, you can write down Hamiltonians where this omega can be exponentially small in the number of.
But in this talk, H is infinite dimensional.
Finite dimensional, sorry. In my talk, finite dimensional. Yeah, thanks.
You just said it, and then the question came. It's exponentially small
in the number. Let's say we have n qubits, exponentially small in the number of qubits. Sorry. All right. So, so this is a problem, right? That to derive this master equation, you need to make this assumption, and this guy can be very, very, very small. On top of that, the jump operators that appear in the equation, they have this form over here, and here you have the eigenstates of the Hamiltonian. So these will be very non-local objects, right? So if you have, like, I don't know, some Hamiltonian on a lattice, these could be acting everywhere, which is, again, something we don't like, both from a, let's say, qualitative and quantitative perspective, because then you have this generator which will be acting on your system globally, which will make it much more difficult to analyze. So, so if you, again, go back and make the connection with classical metropolis sampling, we see that it has the following three very nice features. It satisfies this detailed balance condition I mentioned before, which you can use to show that the Gibbs state will always be a fixed point. But the updates you have to do are also local, in the sense that, for instance, you can do these local bit flips and see how the energy changes, and based on that, you accept or not a flip. Which means it can also do these updates efficiently. And then if we want to take this and apply it to quantum systems, so far it had been very difficult to find proposals that satisfy all of these nice features of classical metropolis. Okay? And for instance, there's the quantum metropolis by Temme, but the updates require a non-trivial quantum algorithm phase estimation, and then you again don't have these local updates. So there were lots of different proposals in the literature. None of them really had all of these requirements. But now we have a possible solution. In fact, now we have quite a few solutions. But as far as I know, this was the first construction of a new Lindbladian that is a quantum dynamical semigroup. And it has almost everything we wanted from the classical. So it has this detailed balance condition. You can efficiently implement this evolution if I give you a quantum computer. But what is the difference between the classical case is that the jumps or the operators you're going to do, they're not local, but they're quasi-local, in the sense that each jump operator in your Lindbladian, it will not act on a constant number of qubits, but it's going to have some sort of tail. So it's you can, as you truncate it to only act on a subset of qubits, you're going to approximate this operator better and better. Okay.
Super quick. So when you say efficient on the quantum computer, so what you mean is that what you have access to physically is e to the IHD.
Oh, that's the next slide. Thanks. So very good question. What do I mean by efficient? So I mean the following thing. I mean that I can implement this time evolution on a quantum computer. So if I want to go up to time t, then I need to have access to Hamiltonian simulation time, which is what you are referring to. So I need to be able to simulate e to the IHT. And I need some other technical details. Maybe I can skip those. But essentially, it tells you that if you're able to implement the Hamiltonian evolution, I can also implement this sort of Gibbs sampling. Does that answer your question?
Are there any requirements? I mean, just very naively. I mean, I'm not from the field, so are there any requirements on the jump operators?
Yeah. So the jump up. I mean, I think that if you.
Locality, in a way.
Pardon?
You're speaking of locality, if I understand you.
Yes. So the way you would usually pick them is, for instance, if you pick them as all single qubit Paulis or 2-qubit Paulis, then you're fine. For instance, so you can pick these operators as only acting on subsets of qubits.
But it's like so the goal is to converge to the Hamiltonian. I mean, to the Gibbs state, and you try to find the best jump operators.
That's a very good question. So it's a very important question that I'm not going to care about in this talk. So I think this is one step beyond. So you could ask, in this talk, I'm just going to ask, okay, is there some set of local jump operators such that this dynamic semigroup will converge fast? So is there a choice? And we're going to show that, like, if you pick all single qubit or 2-qubit Paulis, to be honest, I don't recall exactly, then this is guaranteed for certain classes of Gibbs states. But then you could go one step further and ask, what is the optimal choice of these jump operators? How should I choose them, and so on? So that question is very relevant, but I'm not going to discuss that here today. Does that answer your question?
Yes.
Thanks. Can you one page before?
Yes.
The A alphas, which average with the Hamiltonian, in your example, they are local, right?
Sorry. I mean, I skipped to the next slide and didn't explain this. Yeah, sorry. Yeah. Thank you very much, Marius, for asking about this, because I didn't tell you how these jump operators actually look like, and this is going to be essential. Essentially, what you do is you take like some sort of Fourier, and you take these local jumps and you time evolve them with the Hamiltonian, and you apply a so-called filter function. So in this case here, it's going to be a Gaussian. So you have this extra parameter sigma e. It's going to be the width, right? And what is going on here? As you go to larger times, this f of t is gonna kill the contribution. And there is this tool from quantum many-body systems, which we're going to use extensively throughout this talk, so-called Lieb-Robinson bounds, which tells you that if you start with something that is local, and this Hamiltonian over here is also local, then for short times, it's going to be well approximated by local observables again. So what's going on? For short times, this thing is going to be local, so we're fine because of Lieb-Robinson bounds. And for longer times, this thing over here is going to kill the contribution. And this is why you get quasi-local jumps. All right? Thanks again. Other questions about this? No. Then let's continue. Okay, so hopefully we've gotten to the point where we are convinced that at least in principle we could implement this time evolution on a quantum computer. But the question is, well, okay, I can implement this, but will it converge fast? Can I prepare any interesting states with this? This is precisely the same question that is also asked for classical Markov chains. So there's this whole literature devoted to mixing times, and we're asking essentially the same question for quantum systems. Again, we didn't start the study of mixing times. There's also lots of stuff in this direction. But one approach you can take to show convergence is the so-called spectral gap approach, which is going to show you a statement like this one, that the trace distance between the output of the semigroup, given any initial state, and the Gibbs state is going to converge like this. So if you look, n here is the number of qubits, say. So if you pick polynomial times in the system size, this is going to be very small. So this shows, yes?
So in your figure over there, so the first qubits, are those like auxiliary qubits then?
Yes.
Okay, so the state is then prepared in the channel that contains rho?
So yeah, this bit over here.
Yeah, okay, cool. Yeah.
Yes?
Quick question, if I don't care about the fixed point, does this procedure gives me an approximation of the evolution generated by the original Gibbs generator? So I said it can be efficiently implemented?
If you don't care, no, it's not. So, okay, I don't, in principle, the Davis generator would correspond to doing this, but without having the f of t over here. So I think you just get something different. Yeah.
I guess if I follow this recipe and compare the evolution I was getting from the full peak and these generators versus this, can I bound to say something or something like something?
Oh, I don't know. We did. I think we can show, for instance, that if this thing, I remember that at one point we wrote down a statement like that one. I don't recall the details, and I'm being recorded, so I should be careful in what I say. But I think that I think that for some systems we were able to conclude something like, oh, if this thing converges fast, then the Davis will also converge fast. But I'd have to think more about it. But a diamond norm, that I haven't considered before. Yeah. All right. So what's the spectral gap? So I was saying that you have these get an estimate like this one. What is this so-called spectral gap? Well, it's simple. It's just the smallest non-zero eigenvalue of this generator. And if you go back, this is essentially showing exponential convergence in the so-called chi-square divergence. So yeah, essentially it's like an eigenvalue problem. And this will give you, as I said, polynomial time convergence. So this is just a standard method to bound mixing times. Now, our first result is that for a choice of AA, going back to your question, essentially 1 qubit Pauli's, this spectral gap is a constant. So the C over here is a constant that is independent of the number of qubits. And we can always get this whenever the underlying Hamiltonian satisfies this so-called de Brabantson bound, which tells you that local observables are mapped to approximately local observables in the Heisenberg evolution under H. And this holds for any constant temperature. I mean, not any constant temperature, sorry, for all temperatures below a constant threshold, right? So given combining our first result with what I mentioned before, that you can efficiently simulate those Lindbladians on a quantum computer, this gives you an efficient algorithm for high temperature Gibbs states. Okay, so this tells you that you can efficiently prepare these Gibbs states on a quantum computer. Now, I'm not claiming that this is going to be the killer application of quantum computers. So, but what I do believe is that this shows that this new generator is very promising in the sense that it should, to convince me you have a good quantum Gibbs sampler, you should be able to prove it converges fast in the same regimes where we have classical results. For instance, classically, there are a bunch of results that tell you that at high temperature, metropolis converges fast. So I would expect same things to hold for good quantum Gibbs samplers. And this indeed shows that this is the case.
I have a question because you say that's low temperature or high temperature? Because usually I think that's high temperature.
High temperature.
Okay.
Yeah, so beta is the inverse temperature. Yeah. Yes?
I have a question. So here you have the constant threshold for the temperature. There was a similar work of saying that high temperature Gibbs state is separable.
Yeah. So unlike the other excellent question I was asked, I was going to answer that question at the last slide, so I'm not going to skip all to the end, but I'll address that later. Yeah. By the way, okay, I don't. Okay, so all right, you're all asking very good questions, and I'm not doing great on time, so I'm going to be very quick on this proof, and hopefully to get some time to tell you more about another proof, which I think is more relevant from an optimal transport perspective. But how do we show this rapid mixing? We reduce this sort of dissipative problem to a Hamiltonian problem, and we use this detailed balance condition to map our generator into a Hamiltonian and an enlarged space. So you can show that this thing over here is self-adjoint, and on a Hilbert space that does not depend on sigma or beta. And from this Hamiltonian, and this Hamiltonian has the property that the Gibbs state, the vectorized Gibbs state, is its ground state, and the spectral gap of the Lemblandian is then just the spectral gap of this Hamiltonian. This is also a well-known trick, okay? So it's not like we invented this. But what is nice is that you can use the fact that these jumps were quasi-local to show that this Hamiltonian you get will also be quasi-local in the sense that you have like interactions with exponentially decaying tails. And then what we do is to show that if you let beta go to 0, what we essentially get is the so-called depolarizing channel. And for the depolarizing channel, we understand things like the spectral gap very well. It's very simple to compute. So we know that in the limit beta equals 0, we have a depolarizing channel, and that guy has a constant spectral gap. And the ground states of the polarizing channel is just a maximally mixed state, which satisfies something called local topological order. I don't have time to explain what this is to you, but essentially this means that locally you cannot distinguish. Yeah, okay, no, let's just skip. Sorry, for time constraints, I'm not going to explain this part. But what matters here is that for such systems that are gapped and you have local topological order, you which is like some sort of local indistinguishability, you have very strong perturbation bound results on the gap of these systems. So we can essentially interpret high temperature as a perturbation of the beta equals 0 case and get the gap for these evolutions. All right, moving forward. This also has some nice implications because we can then not only use the Lemblandian to prepare this Gibbs state, we can also prepare a purified version of it, which is called a thermofield double. And there are some connections to things I don't understand at all. Like apparently it's dual to a double-sided wormhole. I mean, I don't know. I'm just saying some words I read somewhere. But people do care about also these purifications of the Gibbs state. And as far as I know, this is also the first result that tells you that you can actually also prepare them efficiently for high temperature. Because we can then do a diabatic preparation using these Hamiltonians we described before. So also for the same temperature range, for the same classes of Hamiltonians, we can also adiabatically prepare the purification of the Gibbs state. All right.
Daniel,
yes.
Quick question. Where does this beta star come from?
Yeah. Okay, I forgot to. You're all a great audience, always keeping me from forgetting some important things I forgot to say. So it comes from this result. So essentially in this result, they show that if you perturb each term of these gapped local Hamiltonians with local topological order by some constant, and this is why it's a non-trivial, very non-trivial result, because like the total size of the perturbation is going to scale with the number of qubits, but you're only perturbing each local term by something that is up to a constant. And the size of this constant where you can do this perturbation and you still keep the gap will be then translated into the beta. Now, so it's coming from this result, but this result doesn't give an explicit constant for how large this perturbation can be. We just know it's of constant order. We were not able to extract it from the proof. So I cannot tell you exactly what beta is, but I'm now going to switch lanes and talk about a different technique to show rapid mixing where we actually get an explicit beta. So I don't care too much about the fact that we don't know it explicitly anymore. Yeah.
Do you expect that it relates to like superconductivity or some other sort of phase transition?
Oh, yeah, another great question. Like, no, I think we're still very far from that. So the actual values of beta where we can show rapid mixing analytically are still far from the phase transition. But I would expect you could, in principle, go all the way there. Yeah. All right. Yeah. Other questions? No, please.
What was the end of that slide? On the next one.
Number of qubits. Yeah. Okay. Okay. So I told you before that this sort of spectral gap approach gives you a mixing time that is polynomial with the number of qubits. Now, this is not what you would expect. So classically, for high temperature states, we know that the mixing time is actually logarithmic in the number of bits or the system size, right? So quantumly, we would also expect this to be the case, and this would be optimal because also for the polarizing channel I mentioned before, we know that the mixing time is like log n. So log n is also, in a certain sense, optimal. So we were interested now in getting this optimal convergence time for these quantum Gibbs samplers and also get some explicit constants for the temperatures you could go to. This would be important not only because of the phase transition question, but also your question before about the Tang result that I'll comment on later. So to do that, we were working with the so-called oscillator norm of an observable, which is defined as follows. So let's say these are your set of qubits. So you can number them from 1 to n. So you take your observable x and you compute the operator norm of this thing. You take x and you trace out one side, replace it by the identity over 2, and you do these for all sides. So if you look at this, yeah, keep maybe this definition in mind, because again, I think that there might be a connection to quantum optimal transport. I guess Milad is going to talk about his nice definition of quantum Wasserstein 1 today. On Friday. Oh, sorry. Yeah, okay. Well, so you have to remember this quite well throughout the week. I hope this formula made a big impression on you now, because it looks kind of similar to some things they do in their paper, so maybe there's some connection there. And you can show the following inequality. So if I let rho t be the evolution of the state under the semigroup, and sigma again the fixed point, and I let xt now be the observable evolved in the Heisenberg picture, you have this sort of inequality. And it's maybe not too difficult to see by a triangle inequality that this thing over here is at most 2n. Oh, I changed notation, sorry. Uppercase, before I was calling the number of qubits uppercase n, now I'm lowercase. But probably this was not the most confusing aspect of this talk. What what is nice is that if we show that this oscillator norm now converges exponentially fast to 0, then of course we'll get a log n convergence for the trace distance. Okay, again, we were not the ones who invented this idea to show rapid mixing. In the classical case, using this oscillator norm goes back to Eizenman and Holly, and even quantumly, other people have used it, but for commuting Hamiltonians. Right? Yeah.
I have a question for this oscillator norm.
Yes.
What if you just replace the sum by the supremum?
Yeah, then I guess you get exactly what, I mean, up to a constant, this Wasserstein 1 distance of Milad and others. So that's why I think there might be some relation. For our proof, it's going to be quite annoying to do that, because if we're to prove this thing, we're going to then take some derivatives, and then sort of the linear the derivative of linear combinations is much, I mean, it's nicer to work with than of the maximum. But I'm not saying it will not work, just that probably this one is slightly easier to work with. But it might go through almost immediately. I haven't really tried it.
Because I followed a classical proof. Basically, what you do is you treat for each side, and you get a like differential inequality, and then you take the sum of all the sides.
Yes.
So I didn't see any difference based on my superficial understanding of this trick.
Yeah, so maybe there isn't really. Yeah, I tried, and I thought that at one point it would be annoying to have the soup instead of the sum, but maybe yeah, we can talk about it later. Would be nice to see. So, but yeah, I do agree though with your feeling that using this proof, it should not be too difficult to show exponential convergence in Milad's Wasserstein distance. So maybe this is a nice problem for this week. And then this would be much closer to the topic of the workshop. All right. So this is going to be our the metric. And how do we show this fast convergence? Well, we again will follow this perturbative approach. So we're going to compare to the polarizing noise. So this is going to be the case beta equals 0, because for the polarizing noise we can show indeed rapid convergence in this oscillator norm. And for technical, so essentially, if you go through these differential equations you were referring to before, you can show that it suffices to have exponential convergence of the oscillator norm to have inequalities like this one. And these coefficients need to satisfy another inequality, which is this, where kappa is the convergence rate in the oscillator norm for the depolarizing channel. Okay, and how do we get, so unfortunately I don't have time to explain to you why these inequalities suffice, but at least I'll give you some intuition as to why these inequalities are satisfied in the framework of Chen. So for the first inequality, well, let's try to understand what this inequality is saying. So maybe you already forgot what these delta A's are. So for a site, these delta for qubit, these delta A's are doing this thing. So I'm essentially like tracing out the observable on qubit A. So for sure, this is only something that acts non-trivially on site A. All the other sites are left invariant. And this here is how the Lembladian is acting on site B. And here is where the quasi-locality of these terms becomes crucial. Because what we're saying is that as A gets further away from B, these things will essentially commute with each other because they're going to act on disjoint sets of qubits. So in a certain sense, as A and B get far away from each other, because we have this quasi-locality, this thing over here is going to get smaller. So this is why you could expect an inequality like this one. And for the second one, well, again, this is some sort of perturbation bound. So we're asking ourselves, how much does the action of the generator differ from temperature 0 to temperature beta? So here we have to derive some perturbation bounds for the L infinity to L infinity norm of these guys in terms of beta. Yes?
I think the right explanation is that this simplicity has to do with curvature.
Yeah. So
That's where it comes from, at least, right?
Yeah. I mean, kappa here is not a coincidence, right? So I agree. Yes. So
Curvature, actually.
Yeah. I agree with you, and it would also be quite. I mean, I don't think it would be an insane amount of work, and maybe you already see immediately how to do it. You from these results also get all the nice things you get from curvature, right? So yeah, another thing we would be very happy to discuss this week. Right, and then this is so we show this perturbation bound in terms of beta, and then you get inequalities of this form. Oh, okay, thanks. And then there's some sort of constant threshold after which the perturbation bounds and these bounds are no longer good enough to ensure that the sum of these terms is smaller than the kappa. And that's how you get the constant threshold. So what I wanted to also emphasize is the fact that the quasi-locality of the generators was quite important to get something like this. Okay, so otherwise you would have no way of controlling this commutator over here. But the fact that these generators satisfy detailed balance, or the fact that the semigroup converges to a faithful state, a 4-rank state, was was essentially irrelevant for this proof. And this observation is important because, for instance, I think maybe 2 weeks ago, there was a paper between the groups of Lin and Presco, where they used a very similar approach to show also rapid mixing, but not for Gibbs states, but ground states of certain fermionic systems. And ground states are then no longer like full rank. And if you don't have full rank invariant states, techniques like spectral gap stop working. So it's quite nice that this technique sort of doesn't care too much about the rank of the fixed point. All right. So again, what we get from all of this is that the Chen et al. Generators, they converge in logarithmic time. If you have a Lieb-Robinson bound for H, as I mentioned before, but actually for some technical reasons, we have a bit more space in the sort of Lieb-Robinson bound we can use in this proof technique, which means that we can also show rapid mixing for Hamiltonians that are not necessarily strictly local, in the sense that only a few local qubits talk to each other, but also for interactions with an algebraic tail. Because we have a bit more breathing space here in the Lieb-Robinson bounds. And again, up to a constant threshold temperature, but this time I can actually tell you what the numbers are. They aren't that great, that's why I didn't put them here. No, just kidding. I would have to introduce some other parameters here, but I would also be interested in improving the numbers again to see to what extent we can get, because the higher the value of beta, at least in principle, the more difficult it should be to prepare these states on a classical computer. But at least I'm not a specialist on classical simulation of quantum Gibbs states, But as far as I know, if you have these algebraically decaying interactions, it's not so obvious if you can do all of them efficiently on classical devices. So this, I mean, again, I'm not claiming that this will be a killer application, but maybe we are closer to the regime where at least it's not obvious that classical computers can compete with quantum ones. All right, so let me conclude. So I showed you that we can, using these Chen generators, efficiently prepare quantum Gibbs states at high temperatures. We showed both the spectral gap approach and also the oscillator norm approach. What is nice about the spectral gap approach is that it also allows you to efficiently prepare this thermal field double state. Now, one very interesting question is there a way to more naturally implement this time evolution? I don't remember, I don't know if you remember, but I mean, maybe slide 5 or 6, I showed you the circuit. It was not very simple. You actually need a full-scale fault-tolerant quantum computer to implement that. But maybe there are easier ways to actually get these time evolutions. So it would be interesting also to investigate in what regimes you have this quasi-local and efficient implementation, or the convergence time is efficient. And this is actually now that, so I should update this slide as well, because as I mentioned before, there's results by the group of Linden and also Presco showing rapid mixing also for some fermionic states, not only at high temperature. So there's been some progress on this. That paper also did some progress on my question number 3, which is how well does it perform in practice? Because, well, you know, the regimes where we can prove things analytically is a bit limited, also classically. We cannot prove these methods work well classically for all the regimes where we know they actually work well. So some people are starting to investigate numerically before we actually can implement this thing on a quantum computer, how it scales for certain systems. Another important question is, what else can we do with these quantum Gibbs states? We are now developing all this machinery to converge to them, showing how to prepare them efficiently. But we do not have that many applications, and we have to be honest about this, of what you could actually do with these Gibbs states, especially at finite temperature. And last but not least, going back to a question we had before, so there, around the time we put out our spectral gap result, Tang et al. Got in touch with us, because they have a classical algorithm that allows you to sample from quantum Gibbs states at high temperature, but at high enough temperature. But actually, when we saw the result, we realized that they had proved something even more amazing, which is that their algorithm actually implied that there is a constant threshold temperature at which all systems that are at a higher temperature show no entanglement at all. So not only were they showing that you can simulate these systems efficiently on a classical computer, they were showing that they're not that quantum, right? So so the regime where we can show rapid mixing scales a bit better in certain parameters than what they can do. So we can certainly go to temperatures they cannot go for certain systems and certain limits. But this does not mean that the regimes we can cover contain entangled states or states that have very complex quantum correlations. So I think it would be interesting to see to what extent we can have this rapid mixing, convergence, and so on, and still have highly entangled states. to see whether this is just one regime that Tang et al. Identified, or whether we can we can go a bit beyond that. So I think that's also a very relevant and interesting question. And yeah, with that, thanks for your attention.